So thanks a lot to the organizers for organizing this and then reorganizing this. And thanks a lot to the IPAM staff for making sure that we haven't yet got Zoom bombed, right? Amongst other. Okay, so since it's a short talk, I thought I would give a quick talk about dissipation enhancement and blow-up suppression. Usually, I guess the previous times I spoke about this, I talked more about dissipation enhancement, but this time, let me maybe talk about the blow-up suppression instead, all right? So it's fitting because I think this problem came from a previous iteration of this conference in 2009, right? There was this talk by Jeff Weiss over there that motivated Sasha to study chemotaxis, right? So let me just introduce this example quickly, right? So the motivating example I'd like to talk about is chemotaxis in the Keller-Siegel equation of this form, right? So the equation is, I look at dt rho minus Laplace rho, and on the right-hand side, I have chi, which is a constant. I'll explain where this comes from in a second, times divergence of rho gradient Laplace inverse of rho minus rho bar. Okay, so let me explain what each of these things are. Rho is modeling the population density of, let's say, an organism, let's say bacteria, right? How does population evolve? Well, normally I have diffusion. So if I have one blob of bacteria, it wants to diffuse out, yeah? But in this chemotaxis model, what happens is, okay, the bacteria secretes a chemoattractant, which is some chemical. And this chemical is sensed by the bacteria, and the gradient of this chemical potential drives the evolution, right? So the density evolves, and there's a bias. The bias is directed by response to this chemical stimulation, right? So if you choose chi to be positive, it's chemoattraction. It drives bacteria inward towards regions of high concentration, right? That's the nonlinear term, right? And that's the case that I'm going to look at, right? So this is a sensitivity parameter. And for me, for simplicity, I want to do this on the torus. So periodic boundary conditions, in order to ensure that I can solve these equations, rho bar is just simply the integral of rho, spatial mean. So I take Laplace inverse of rho minus rho bar, and this makes sense, okay? So the various versions of this, I guess, let me go back to some work of Jaeger and Lukehaus in the 90s, right? Who studied this equation, and they had two nice results, right? So first, if you start with small initial population, then everything is fine. You have global existence, right? Then they exhibited examples of blow up when the initial population was large. And of course, there's a huge following. People have studied this in various ways since. Sorry for not mentioning everyone, but let me mention maybe just three results. One was this Blanquette Carrillo-Masmoudi in 06, Blanquette Dolba-Pertham 07, and then I guess Donghi Wei a couple of years ago as well, right? In 2D, there's this nice phenomenon of a sharp blow-up threshold, right? Which is if your initial mass is greater than or equal to 8 pi, the equation blows up. If not, it stays globally well posed. Okay. So, all right. So a question I'd like to ask in this mixing workshop is, can I use stirring to affect the blow up, right? Can we stop the blow up with stirring? So let me do that here, right? So I took the same old Keller-Siegel equation, and you see the only thing I added was a convection term. And for me, I'm going to always assume that U is smooth and divergence free, so incompressible, modeling stirring of an incompressible fluid. Okay, can you stop the blow up? Well, there are a couple of nice results, right? So there's a result by Jacob Bedrosian and Siming He in 2017. So what they did was they looked at this in 3 dimensions, and in 3 dimensions, they added a shear flow, a one-directional shear flow. So what happened as a result of this is that you can reduce it to the same blow-up threshold as in 2 dimensions, right? You get exactly the same, like more than 8 pi, you have blow-up. If not, no. The paper that's more along the lines of what I want to talk about is this paper by Sasha Kiselev and Xiao Xu in 2017, right? So what they had was two families of velocity fields, right? Such that given any rho, right? Given any rho naught, any initial population, doesn't matter if the mass is big or mass is small, it doesn't matter, right? So no matter what rho naught is, you can choose a velocity field u from either of these two families, such that if you stir along this velocity field, you stop the blow up, right? So you avoid these population explosions in little points, yeah? So these two velocity fields, one was these relaxation enhancing velocity fields, which I'll talk about in a bit. The other one was this family of fields studied by Andrzej Latosz and Yao Yao, right? I'll mention those briefly again. Right. There's also some other results by Simming, he, and then Simming, he, and Tadmore, right? But I'd like to revisit this problem and talk about a result of me, Xiao Xu, and Andrzej Latosz last year, right? Which says the following, right? I'm going to define tau star to be the dissipation time of U. I'll define this in a second in the next slide, but roughly speaking, here's what it is. Solve the linear advection diffusion equation for time tau star. After time tau star, the norm of this operator from L2 mean 0 to L2 mean 0 is bounded above by half. Okay, so I'll say this again in the next slide. Okay, so let's call tau star the dissipation time. Okay. Our result is that I can always find you a small tau naught. Okay. This tau naught only depends on the size of the initial data, right? Such that if tau star is less than tau naught, then no singularity. You have global regularity of Keller-Siegel. 2D, 3D, doesn't matter. Okay. So how does this work? Let me just say what this dissipation time is a little bit more carefully. Right? So to define tau star, let's just look at the advection diffusion equation, no nonlinearity. dt theta plus u dot grad theta minus Laplace theta equals 0. So this is just temperature in a fluid and I'm stirring it. Okay, let's assume periodic boundary conditions and mean 0 initial data. All right. So since divergence of u is 0, I can just Poincare inequality this. Multiply by theta, Poincare. What do I know? L2 norm of theta decays exponentially. The rate is the principal eigenvalue of the Laplacian, right? So convection may improve this a lot, right? Because what does convection do? It moves energy to higher frequencies. In higher frequencies, Laplacian works better, right? So with this, let me define this dissipation time, tau star, right, to be the smallest amount of time you need to wait so that you've lost half your initial L2 energy. So these are both L2 norms, right? Let's say you start this equation at time s, run it up to time t. So the time you've waited is t minus s. I want energy at time t to be half energy at time s. Okay. So clearly, this dissipation time, okay, up to a constant, maybe I forgot a log 2 over here, right? So clearly this dissipation time is like 1 over principal eigenvalue of Laplacian up to some log 2, right? Can you do better? Well, yes, right? Whoops. Okay, so just a quick reminder. The theorem that we had was that if the dissipation time is super small, then there's no blow up, right? So to use this theorem, what do I need to do? I need to produce many velocity fields with arbitrarily small dissipation time. Can you do it, right? Well, there's this paper that was already mentioned this morning of Konstantin Kiselev, Rizhik, and Zlatosh in 2008, which when U is time independent, they have a nice characterization, right? They say, if U dot grad has no eigenfunctions in H1, if and only if, right, I look at the dissipation time and that converges to 0 as a goes to infinity. Yeah. So as soon as you can produce flows that satisfy this criteria, you can find lots of velocity fields with arbitrarily small dissipation time. So as a consequence, if U is weakly mixing, then the dissipation time of U scaled by some large amplitude converges to 0 as the amplitude goes to infinity. Okay. Well, of course, there's no rate. We decided to look at this, revisited this with my student Yuan Feng, with my former student Yuan Feng, right? They say, well, if you want to get a rate, you can do it, but it depends on the mixing rate of U, right? So let me not go into what that is, but let me just at least state the result. If U is mixing at a particular rate, right, then I can write down an explicit bound for the dissipation time, right? I can write down that the dissipation time when you take the velocity field U and rescale it, right? So I speed up time by a factor A, increase the amplitude by a factor A, right? What's the dissipation time? It's 1 over A times some big thing, capital H. What's capital H? I can write down capital H explicitly in terms of the mixing rate of U, right? Well, it's not so you have some implicit equation here to solve, but okay, if I know the mixing rate, I can solve that and figure out what capital H is, right? So if, for instance, U is exponentially mixing, what does this work out to? It's basically log square of A divided by A, right? Then there are also these examples from this paper by, let me also mention, there's also this work by Cotizalati, Delgadino, and El Guindi that also has this log square A over A bound. There are also lots of examples in the random case by Jacob Bedrosian, Alex Blumenthal, and Sam Pushon-Smith, right? There's a whole bunch of random velocity fields that get you a dissipation time, which is of order log A over A. Remove the square, right? And then there was this talk of Christian Seiss and Camilla Nobili this morning says that you can't do better, right? There's also this old result of Poon, if you're smooth enough, you can't do better. And this result of Miles and Doering, right, from 18, saying you can't do better, right? But regardless, the issue about this is that, okay, if you know something about the mixing rate, all right, then you can rescale the velocity field and make the dissipation time as small as you want. If you make the dissipation time small, then you can stop the blow up in your favorite equation, right? The thing I didn't like about this was that, okay, constructing these mixing velocity fields is hard, right? Some of them, okay, if you want to do a purely deterministic construction, actually doing a smooth deterministic construction, this is open on the torus. Smooth time independent is still open, right? So there's an example of Andrej Latoš and Tarek El Guindi, which is time periodic but rough. And then there are all these examples here, which are random in time but smooth, right? There's also examples of Anna, Gianluca Crippa, Giovanni Alberti, right? So there are all these examples, but they're complicated, right? All we need to stop blow up, right, is small dissipation time. We don't need mixing. It's a much weaker condition, right? So can you find simpler examples? Well, yes, cellular flows, right? What if I take a strong enough and fine enough cellular flow? I should be able to make the dissipation time arbitrarily small. Once I make the dissipation time arbitrarily small, I should be able to stop the blow up, right? So I'll say a bit more about this towards the end, right? What time do I stop, Anna?
At 30, you have another 10 minutes, 11
10
minutes.
minutes, okay.
Yeah. Speaking.
All right, so what's the idea behind the proof, right? The proof is, once you phrase it in this language, the proof is actually extremely simple and straightforward, right? So let me show you what goes into this proof, right? So quick reminder, right? My theorem is that if dissipation time is small, then there's no blow up in the Keller-Siegel equation, and that's the Keller-Siegel equation, okay? So here's the idea behind it. Let me just rewrite this Keller-Siegel equation in the following form, right? Let's set theta equal to rho minus the average, Okay, write down an evolution for theta. I get dt theta plus convection minus Laplace theta equals some nonlinear function. So this nonlinear function is whatever that is on the right-hand side. Okay. So, okay, so first lemma is, okay, if I have a maximal interval of existence, let's call 0 to t the maximal interval of existence. If there's a blow up of this equation, then you can see the blow up in the L2 norm, right? Which is as you approach the maximal existence time, the L2 norm should blow up, okay? And you can prove this just by the standard calculus inequalities, Gagliaro, Sobolev, Nirenberg. Okay. So lemma 2, right, again, which is standard calculus inequalities, right? For some small time, right, if I start with L2 initial data, for some small time, which doesn't depend on U, no matter what U is, the L2 norm doesn't double. Okay. This again is believable because, well, for the Keller-Siegel equation itself, right, I can certainly prove this result. What if I add convection? How do I make sure it doesn't depend on the convection? Well, the convection term, which I conveniently forgot here, is plus u dot grad rho. Well, the convection term, when I multiply this by rho and integrate, that goes away. There's no u dependence. So I can happily do this, right? All right, so once I do that, right, here's how I'm going to stop blow up. All I need to do is convince you that the L2 norm of theta remains bounded globally. Okay. So let me split analysis into two cases. Right. So here's the equation for theta. I rewrote it. And let me split the analysis into two cases. Suppose 1 over tau star times integral 0 to tau star of the gradient square is large. Now, why am I doing this? Well, let me take a look, right? So dt theta u dot grad theta minus Laplace theta equals n. How about we just multiply this equation by theta and integrate? Okay, so do that. Convection goes away. Laplacian gives me gradient of theta square. What does the nonlinearity give me? Well, okay, this is integral of theta times n of theta. Suffer with some Gagliaro, Nirenberg, Sobolev. See what you can do, right? Well, let me bound it by half times norm gradient theta, L2, plus some function of a lower order norm. I think I can choose f to be like norm of theta L2 to the 4th power, but it doesn't matter, okay? Some function of an L2 norm, all right? So now you see this guy here, I can hide inside there, inside norm gradient theta square on the left-hand side. Yeah. Now, amongst the rest of it, well, I'll say if what's left over beats this function f, then certainly my L2 norm decreases, right? So that's my case 1. So if what's left over, right, beats the function f, then the L2 norm decreases. I just wrote it in an integral way just for symmetry with the second case, right? So I integrated in time divided by tau star on both sides, okay? What if it doesn't, right? So what if the 1 over tau star integral 0 to tau star of gradient theta square is bounded above, right, by this right-hand side, which is 1 over tau star integral 0 to tau star, some function of the L2 norm. Right, so this f is in this case norm theta L2 4th power, for instance. Right. Well, what do you do here? Well, here's the idea. You say, well, let me write down theta at time t using Duhamel's formula. Okay, so theta at time t is equal to solve the linear equation for time t and then put the time convolution guy in. Right, so S is just solution to the linear equation. Okay, now let's take L2 norm on both sides. And here's the point, right? This is just basically the one idea. So if I take L2 norm on both sides, what happens? The first term, if I go up to the dissipation time tau star, the first term gives me a half, right? Because that's the definition of dissipation time. In time tau star, I've lost half my energy. What's the second term? Well, the second term is integral 0 to tau star of the nonlinearity. Put the L2 norm inside. if I can bound this guy, I'm in business, right? So I say, okay, integral of the nonlinearity, let me rewrite that. It's tau star times 1 over tau star times integral 0 to tau star of nonlinearity, right? Oh, great. How can I bound this? Well, first, let's use our Gagliaro-Nirenberg-Sobolev trickery and say, how can I bound L2 norm of the nonlinearity? Well, L2 norm of the nonlinearity, typically I can bound by H1 of theta, right? Plus a bunch of lower order norms. Normally this is depth. I mean, what do I do with the H1 of theta? But hey, look, we're in case 2. H1 of theta, I assumed, is controlled, right? So if I use the standard Gagliaro-Nirenberg bounds on the nonlinearity and the fact that, hey, look, I have a bound on the H1 norm, this entire term in parentheses is controlled by something nice, right? And you have a tau star left out in front. So if I can take tau star times whatever the bound I got for that guy is and say that that guy is less than half the initial data, I'm in business. And that's exactly how you prove the theorem, right? You have tau star times some function of the initial L2 norm. If tau star is smaller than whatever this is, and this function you can compute explicitly, you have exponential decay to 0. Okay, so this works happily in general, right? So this is the way we phrased it in our paper, right? I say, it doesn't have to be Keller-Siegel equation. Give me any equation with some nonlinearity on the right-hand side. What are the properties we use of the nonlinearity? Well, it takes H1 to L2 mean 0, right? And you need 2 bounds, right? So one of the bounds, which I just used on the last page, was if I looked at the L2 norm, I can control it by the H1 norm and some function of a low norm, L2 norm, right? The other bound I used was if I take phi and multiply by the nonlinearity, I can get 1 minus epsilon times the H1 norm, right? I use that in the first case for the energy inequality. Whatever I got from here, I had to hide from the left-hand side, right? So this bound of phi times the nonlinearity, I need a constant less than 1. For the second, the L2 norm, I can have any constant, doesn't matter, right? So if you do this, the L2 norm has to stay uniformly bounded. If the nonlinearity is f, if the functions f and g vanish at 0, then you also should have exponential decay, right? Let me maybe, so I have 5 minutes left. Is that right?
Yeah, more like 2, 2 or 3.
Right.
Yeah.
So I wanted to talk about the Carliad equation as well. I seem to have grossly messed up my time estimate. But let me say briefly what this is, right? So this is something we did after that with Jean-Luc Default, Yuan Feng, and Yu Feng, right? So what's the Carliad equation, right? So, well, here are plots of what it looks like. It's to model phase separation in binary alloys, right? So officially the equation is time derivative C plus Laplace square of C is equal to some constant d times Laplace of C cubed minus C. So what's happening here is C is the normalized concentration difference between 2 phases. D and gamma are 2 parameters. Okay, so the thing about this equation is you have a lot of equilibria, which is just constants. All of them are unstable except for the pure phases, C equal to +1 and C equal to -1. Okay, mass is preserved, so whatever mass you start with stays constant. I'm going to solve it again in the torus with periodic boundary conditions. And the typical pictures you see are here, right? I start with really high frequency initial data, and as time evolves, you start getting these characteristic ridges, right? So can we do the same thing? Let's add convection into the mix. Can you stop these large scale separation, the phase separation from happening? Can you just stay mixed? Well, the answer is yes, but it works differently. We can't use our theorem from before, and you need a stronger assumption, right? So there's a bit of an issue. So I chose D and gamma to be 1, okay, just for simplicity. Add in convection. So here's the U dot grad C. Can I choose U to stop phase separation? So, well, okay. So here's the deal. So instead of Laplacian, now I have 2 Laplacians. Fine. So instead of the dissipation time with one Laplacian, let me talk about tau star alpha to be the dissipation time with alpha Laplacians, right? Just increase the diffusion to that power, right? The assumptions that we had in our previous result just aren't satisfied with this nonlinearity. We can't use it, at least in 3D, right? But if you go through, a similar sort of proof works out, and here's the result you get. If you remember, before I said, if the dissipation time was small, then you had no blow up. In this case, if the dissipation time times the square root of the C1 norm of U is small, then you have no phase separation, right? It's this square root of norm U C1 extra that causes a couple of trouble, all right? So, I mean, first, it's crucial that you have a square root exponent here. If I went through this analysis and I told you that norm of U, C1, times tau star needs to be small to apply the theorem, I am bankrupt. This guy here can be bounded below uniformly. You can never make this arbitrarily small. You're in trouble, right? But the fact that you have a square root saves you, right? In fact, it turns out if U mixes faster than rate 1 over t, you can always rescale it, right? So that you can make the thing that you want arbitrarily small. There was also a similar result by Anna and Yan Feng for the Komatov-Shevchinski equation, right? So I was going to go through the proof of this, but I'm out of time, so let's not do that. Let me just mention, right? So I promised that cellular flows, we have a bound. And okay, so I don't know if I want to go through this bound in detail, but what's a cellular flow? Well, a cellular flow basically looks like this. So here's a stream function, right? Let's say sine x, sine y. Scale it so that this size is epsilon, right? Multiply it by big large numbers so the velocity field is fast. If you do this, right, you can always make the dissipation time small enough, right? This is a theorem that we had in the paper with Andre. Whoops, okay. So this should have been Andre, Xiao, and me, right? The bound is unfortunately not as explicit as I would like, right? Our final result is there exists a scaled cellular flow with arbitrarily small dissipation time. I think the bound is much better. I think actually if you take a cellular flow and write it in terms of the Peclet number, the dissipation time is bounded by 1 over Peclet number raised to 4 over 3. I can tell you where the scaling comes from. I cannot prove it, right? If I want to go from 1 Laplacians to 2 Laplacians, I believe this dissipation time should still vanish. I don't know how to do it, right? In fact, I mean, abstractly, I could like to bound dissipation time with 2 Laplacians in terms of dissipation time with 1 Laplacian. It's possible to get a bound. Here's the bound. But this bound is useless. It's fantastically bad, right? So anyway, there are tons of open questions in terms of lower bounds, upper bounds, mixing times, effective diffusivity, even magnetic dynamos that I don't know how to do. But let me stop. Sorry for going a little bit over time, right? And thanks for your attention.